Hello everyone, I'm Seung This presentation summarizes our team's hydrogen safety design for a lab-scale AEM electrolyzer. Our system uses a 1 weight percent KOH electrolyte and operates at 50 degrees C and atmospheric pressure. Today, we'll analyze the main hazards, identify mitigation strategies, and show how a real incident helped refine our final safety design. The first and most critical hazard is internal H2O2 crossover across the stack. If the membrane is damaged by overheating, pressure imbalance, or dehydration, hydrogen and oxygen can mix inside the stack and create an explosion risk. Our main mitigation is continuous pressure, temperature, conductivity, and liquid level monitoring with alarms and automated shutdown. This way, abnormal conditions are detected before crossover escalates. The second hazard is hydrogen leakage from tubing and fittings, especially in a lab-scale system where repeated assembly and disassembly can weaken sealing quality. A related hazard is air ingress and unintended mixing during startup or shutdown when residual hydrogen and oxygen may remain in dead volumes. Both hazards increase ignition risk and are addressed through gas-tight fittings, nitrogen leak testing, and purging before and after operation. The fourth hazard is hydrogen accumulation in the lab environment. Because hydrogen is so buoyant, it can collect at high points if ventilation is poor. To reduce this risk, hydrogen and oxygen should be discharged through independent vent lines with cold traps used to prevent condensate blockage. All discharge should be routed outdoors or to a high dilution exhaust system, and hydrogen detectors with alarms must be installed in case of indoor accumulation. To improve our safety design, we studied a real incident, an electrolyzer restart at a refueling station. During gas generation, a loud bang was heard and a water vapor cloud was seen from the oxygen vent line. The investigation found a crack in the stack bottom end plate foil, which caused internal H2O2 crossover. Detection set points had also been altered from the defaults, so the leak was not automatically flagged. This incident showed us that engineering controls alone weren't enough. We added procedural safeguards by locking alarm thresholds under MOC protocols so safety logic cannot be casually altered. We viewed system restart as high risk, so restart should only occur after purging, leak checks, and verification of safe process conditions. Finally, although the reported defect was a crack in the foil, the broader lesson was that any compromised sealing barrier can enable hazardous crossover. Therefore, seals and gaskets must be chosen to meet relevant ASTM and ISO standards. From this, we developed the PDRR, prevent accumulation, detect it early, respond automatically, and restart only under safe conditions. In hydrogen systems, the goal is not only to avoid danger, but to control it before it escalates. Thank you.